Hello, my name is Brandon Carter, and I'm a PhD student at the University of Michigan in the Material Science and Engineering Department. My research focuses on growing materials for lasers that can be used to make the internet faster, better, and more reliable. So, with that, I'll begin my talk. I think most people would agree without a doubt that a faster, more reliable, more widely accessible internet is a good thing. So, why doesn't our current internet always have these properties? So, let's take a step back and discuss why that is. Most of our internet data is transmitted through a crisscrossing network of wires right now. And wires are great, but over long distances, our data can become weak. The internet signal can become weaker along these wires, leading to a slower and less reliable internet service. So the natural solution is to look for a technology that can send our signals over long distances without having this weakening signal effect. And one of these technologies, it's been around for a while, is known as fiber optics. And this uses light instead of electricity to just perform the task of sending our data. So the idea of using light to improve the internet sounds kind of exotic, but it's actually quite simple. If you look at the figure on the right, it works by taking a glass-like, clear, or transparent, what we call a fiber, and shining a light or a laser through it. And this laser gets trapped in the fiber. It reflects off the edges of this fiber such that not a whole lot of the signal leaks out, even over long distances in most cases. And since the signal doesn't leak out, nothing is causing it to weaken, meaning that now if we can implement this to send internet data and information, we can send our internet over long distances and not have this weakening effect, making it better than the status quo. In addition to this, light can travel through these fibers at about 100 times faster than electricity can be sent along electrical cables. So we can get faster and more reliable. Before I move on, I would like to say that fiber optics is an existing technology. It's been around for a while. Even a lot of people are familiar with this kind of novelty lamp on the right. You see the light source at the base and the light travels along the fibers and you see it at the edge. It's the same exact technology. So it's not insanely complicated. It just hasn't been implemented in internet service in a widespread fashion. So why is that? Why hasn't it been implemented in a widespread fashion? Well, it turns out that it's not quite as simple as just shining a laser through any clear cable. The light that the laser generates needs to be of a very specific type of light. And if it's not exactly that type of light, you see at these reflection points off the edges of this fiber, it's kind of hard to see here, but a little bit of the light will leak out. And when you send that light over long distances, as you would in internet applications, it reflects more, and if it a little bit leaks out at each reflection point, you get a weak signal, and it doesn't work any better than, say, an electrical cable. It could even work worse. So that's where my research comes in. I create materials that can be used in lasers that can generate that exact type of light we're looking for. So how we do this is we start with gallium arsenide, which is a common material system used in electronics. But gallium arsenide alone can't be used for lasers that make this light. But what we have found is that when you add bismuth, you get closer to that light that you're looking for. And once you get to 10% bismuth, so 10% bismuth, 90% gallium arsenide, you get to the exact light that you want, such that basically no light will exit or leak out of this fiber along as it travels, which is great because that means your internet signal is strong from when you send it to wherever it needs to go, and it's getting there faster because, as I said, it can get there about 100 times faster. So, sounds simple. All we need to do is get 10% bismuth in our gallium arsenide and we're golden. But it's not as easy as it may sound. Turns out that gallium arsenide is a crystal. And for the purposes of understanding my talk, all we need to know is that we have these little atoms of gallium arsenide and they're arranged and they're placed in very fixed positions and they repeat and they do not like to move from those fixed positions. So you get this kind of grid of atoms. And for bismuth to incorporate, bismuth is a very large atom. It needs to push those atoms out. And the gallium arsenide push those atoms around, kind of bending this grid around it. And gallium arsenide, the crystal, doesn't really like that. It fights back, and it fights back in a way that it kind of tries to make sure bismuth can incorporate it and pushes it out. So it's difficult to incorporate bismuth. Well, we have found out that we can incorporate it. We just have to supply a lot of bismuth, and only a small amount of the supplied bismuth actually incorporates into gallium arsenide. But this generates its own set of problems. Since only a small amount of the bismuth that we supply incorporates, a lot of it just kind of builds up on the surface of the samples we're growing and forms these droplets. You can see this on the left here, which we have these little rounded abstract shapes are bismuth droplets. And at first glance, we might just think, well, just cut those off the surface, and underneath, you'll have your sample, and hopefully you have 10% bismuth. We can actually get over 10% bismuth. We've gotten up to about 22, 23%. So 10%, like, we can get that pretty easily. But it turns out that 10% bismuth isn't a uniform incorporation. In one part of the film, it might be 25%, in another part of the film, it might be 0%. And we can see that here on the picture on the right. This really bright dot up on the right, the top hand corner, that's just one of the bismuth droplets. And the film is directly underneath that. And what we see is these brighter regions of the film correspond to a lot of bismuth in the film, and these darker regions correspond to not a whole lot of bismuth in the film. It could be even 0. And while this might average out to 10%, each region has its own incorporation, which means that it's going to generate a different type of light, and each type of light is going to behave different in the fiber optic cable, and that's not what we want. We want 10% evenly distributed all the way through the film, such that it'll work best for fiber optics. Unfortunately, we're still working towards that. We are changing how we grow these films, hopefully to lead to this uniform composition. That is a current area of research, and we are still working on it. But hopefully, we can achieve our goal of getting this 10% incorporation uniform through it, and we can make some lasers and that hopefully will lead to faster, more reliable internet in the near future. That is the conclusion of my talk, and I'd like to thank you for listening.